Welcome to Math TV with Professor V. This is video lecture for section 2.2, properties of matrix operations for linear algebra. And in this video, we're mostly going to be working through proofs. So if that's something that you struggle with, then you'll probably really benefit from this video. So first, we're going to kick things off with a theorem, theorem 2.1, properties of matrix addition and scalar multiplication. So if capital A, B, and C are M by N matrices, and C and D, notice those are lowercase, are scalars, then the following properties are true. So property 1, we have that A plus B is equal to B plus A. So what that's telling us is that matrix addition is commutative. Okay. Second property, A plus the quantity B plus C is equal to the quantity A plus B plus C. This tells us that matrix addition is associative. And then notice here for property 3, we have multiplication with two scalars and matrix A. So C times D, those scalars multiplied, that quantity times matrix A is equal to the scalar C times the quantity scalar D times A. And then property 4 is a little interesting. You may not have seen this before. Capital I times A is equal to I. So we'll talk a little bit more about I in just a minute. If you've never seen it before, I is the identity matrix. And for example, if you have a 3 by 3 square matrix, the identity matrix for it would be I, and then we put a little subscript 3, and it would look as follows. It would have 1s on the diagonal and 0s elsewhere. And we'll study the identity matrix of different sizes more in just a minute. But keep in mind, like pretty much every operation has an identity operator. Like if you think of just addition with real numbers, 0 is the identity operator. If you add 0 to any number, you get the original number. For multiplication, that number is 1. 1 times any number is the original number. So pretty much every operation has an identity operator, and you'll kind of study that in abstract algebra more when you take a step back and look at operations from a more generalized perspective. Okay, getting back to the topic at hand, property 5, we have a distributive property. So C, remember that's our scalar, times the quantity A plus B, those matrices would be CA plus CB. And then property 6, that's the one that we're going to prove right now. The scalar C plus D times matrix A is equal to C times A plus D times A. So let's prove property 6. And what I'm going to do, I can't assume that I know what the size of matrix A is, right? So I'm just going to have to let it be some M by N matrix. So I'm going to let matrix A be defined as follows. So first entry here would be A11, then A21, all the way to AM1, showing that it has M rows. And then the next column would be A12, A22, down to AM2. And then I don't know how many columns there are. I'm going to leave n many. So you'd have A1n, A2n, AMN. Honestly, this is the hardest part of the proof, just writing these out, because it's a little tedious, you know, but you can handle it. It's not the end of the world. Okay, so what are we trying to do? Show that the left-hand side is equal to the right-hand side. Let's define what C and D are. So we're going to let C and D, remember these are scalars. What does that mean? That means they're not matrices, they're not vectors, they are real numbers. So that means C and D are elements of or belong to the set of real numbers. Okay, define all your quantities. So now let's start off with the left-hand side. We have that the scalars C plus D times matrix A. Okay, we're going to manipulate that using how we've defined matrix A here, and see if we can play around with things and get the right-hand side of that property. Okay, so C plus D times A would equal C plus D, and then now I'm going to write out the matrix that I have that represents A, that's size m by n. So A11, A21, all the way down, A12, A22, keep it going, A2n, AMN. Okay. So, how does multiplication of a scalar by a matrix work? Well, we've looked at this a little bit before. You take each element in the matrix and you would multiply it by the scalar quantity outside. So what would we have in the next step? Well, we would have the following. Give yourself some room, okay? You're going to have C plus D times the first entry, A11. Then you would have C plus D times the next entry, A21, all the way down to C plus D times AM1. And yeah, usually I do write out like the first two columns, and then you can put dot, 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 okay? And then first two rows usually. This would be A22, C plus D, right? That scalar gets multiplied by every entry in the matrix. When I was first learning matrices, the Matrix movie had not yet come out, and then it did. And then my dad would always make fun of me and quote lines from the movie because he didn't really study advanced mathematics. Okay, C plus D, AMN. Here we go. All right. So what we're going to try to do now is break this up into two matrices, because keep in mind, look at property 6. Right? I started with the scalars C plus D times matrix A, and I want two matrices on the right-hand side. So we're going to get to where we're going to break all this up. All right, well, first thing I would want to do is apply the distributive property, just for real numbers, because now these are all scalar quantities inside here. So I'm going to distribute and open up those parentheses inside for all the terms or entries in this matrix now. So what are we going to have? Good. This is going to be C A11 plus D A11, C A21 plus D A21, C AM1 plus D AM1. Keep going. Okay. CA22 plus DA22, CAM2 plus DAM2. Last one. CA2N plus DA2N. And all the way down. If you're bored, this is what I always tell my students, be grateful, because you know what? There's days where you're sitting in math class so lost, unawares of what's going on, and you'd be like, oh my goodness, there was a time when I was bored and I didn't appreciate it. Okay? Keep that in mind. All right, good. Things are looking great. Remember, we want to have two matrices at the end. We want C times matrix A plus D times matrix A again. So it seems natural. I'm actually going to break this up into two matrices at this point, since every entry in the matrix involves addition. You can split it up like so. All of the terms with C are going to go in the first matrix, and then all the terms with D are going to go in the second one. So we'll have CA11 here, CA21 here, CAM1, CA12, CA22, CAM2, and then CA1N, CA2N, CAMN, plus Looking good. dA11, dA21, dAm1, dA12, dA22, dAm2, and then this is dA1n, dA2n, damn. Okay. And then we're almost done. Remember, the goal was to have C times matrix A plus D times matrix A. Keep the goal in the forefront of your mind. So I'm going to need to factor out the scalars C and D from the matrices. And you guys, if you're like, oh, this is so obvious, why do we have to do this? That's the whole point of a proof, okay? It's not, the things that you're proving are true statements. So it's not like, oh, it's up in question whether or not this is valid. No, you're just there verifying, going through the logical process, creating a mathematical argument. Okay, it's a technique, it's a skill that you need to develop. And then, you know, you can work on proving things that haven't been proven if you so fancy later in life. But don't think for 1 second, this is groundbreaking. It's supposed to be obvious a lot of the time, especially when you're doing very elementary proofs and you're just building your skills. Okay. A1n, A2n, AMN. Plus D. Now, obviously, like these kinds of proofs with all these matrix entries are extra tedious. All right, I'm not gonna lie. They're not my favorite. But I'd rather do this than write an essay, for sure. Okay, almost done. A1n, A2n. Try to make it as aesthetically pleasing as possible, you know? Like, oh, this is so repetitive. We'll make it look pretty. Do something nice. Boop, there we go. And then we're done. We have to still write out exactly what the right-hand side was. C times, that's matrix A, yes, plus D times matrix A. Bam. Good job. Good job. Okay. A couple more definitions and terms. So the zero matrix is denoted by 0 with subscript mn, and it is the additive identity for the set of all m by n matrices. Okay, so here's some properties of zero matrices. If we have A, which is an m by n matrix, and C is a scalar, then the properties below are true. So A plus 0 matrix, okay, is equal to A, just like with real numbers. A plus, this is the opposite of A, gives you the zero matrix. Opposite of A is also called the additive inverse of A, okay? All the terms would have the opposite sign. And then 3, if a constant, C, a scalar, times A equals the zero matrix, then either C is 0 or A is the zero matrix. Okay, so you have like a zero product property situation going on. And then we have properties of matrix multiplication. We already saw previously, remember that matrix multiplication is not commutative, but we still have some properties that hold. So A, B, and C are matrices with sizes such that the matrix products are defined, okay, so that you are able to multiply them as follows. And then C is a scalar, then the following properties are true. So 1, matrix multiplication is associative. Notice the order is the same though. We know matrix multiplication is not commutative. Property 2, we have a distributive property of matrices. Again here, this is associative, different from 2, but still distributive. And then 4, we have here a scalar times matrix product AB is equal to scalar C times matrix A and then multiplied by B, or you could take matrix A and then multiply by the product scalar C times matrix B. So the scalar you can kind of move around, but the matrices you cannot. Okay, so what we're going to prove right now is property 4. And we have to make sure that the matrix multiplication A times B is well defined. So we're going to prove property number 4 right now. So we're going to let A be an M by N matrix. We don't know what size it is. And then B doesn't need to necessarily be the same size, but in order for us to be able to multiply A and B, remember the number of columns in A has to match the number of rows in B. So we'll say matrix B is an N by P matrix, okay? So we could represent matrix A. We don't have to do all the dot, dot, dots this time because we can do the proof just by looking at like an arbitrary row times column of the multiplication. So I could just say matrix A is represented by, remember, you can write lowercase a sub ij. And then matrix B, similarly, you just use lowercase ij to show it's just some arbitrary entry, okay? So if we're going to look at the multiplication of just one element, one entry of that matrix AB, so remember, if we're looking at matrix AB, I'm going to look at row I of matrix A multiplied by, you would have column J of matrix B. How would it work? So AB would equal AI1 B1J plus AI2 B2J plus all the way down to AIN BNJ. If you can't see that, that's okay. That's why we write out the matrix the other way with all the dot, dot, dots. And this is just one element. This is not like all of matrix AB. This is just one element of AB. So you might be thinking, where on earth am I getting that from? If you can't see it, then let's just go back and write out more expanded form of matrix A and B just to help you visualize, okay? So remember, matrix A is size M by N. So we've written this out before. This is optional, just in case you can't see how to get this expression here, okay? So we've written it out, A11, A21, all the way down to AM1. And then remember, we had like A12, A22, AM2, oops, 2. And then I do want to add in something that we didn't write in the last proof because I'm taking an arbitrary row from matrix A in just a second. So I'm going to write, if this is A1, 2, then what would I have next? A1, 3, A1, 4, etc. Okay, so this would be A1, and then this is column, oh, let's just go to N, that's fine. A2N, AMN, okay. What I needed to do is add in some arbitrary row. That's what I need to do. So maybe I'll add it in here. So you do a little bit of dot dots, a little bit of dot dots, and I have to write out arbitrary row I. Maybe I need more space. Okay. So you're gonna have AI1, AI2, all the way to AIN, and then you can keep going how we normally have AM1, AM2, all the way to AMN. Okay, so I'm adding in basically what's new. What did I not write out in the last proof? This row I. Okay, so this is row 1, row 2, row 3, 4, 5. This is row I right there. And then keep going, we don't know. And then that's the last row, row M. Okay, that gets multiplied by matrix B. Ooh, that's too aggressive. That's going to get multiplied. So this is matrix A. I wrote this out just to help you see. That's going to get multiplied by matrix B. So let's do the same thing with B. So we've got B11, B21. B has n rows, so this would be Bn1. Then this would be B12, B22, and then this would be Bn2. And then I want to show some arbitrary column J. So you would have B1J, B2J, Bnj, and then you go to the last entry, B1P, B2P, because it has P columns, remember? Bnp. Okay, so this is matrix B. All right, so then what we do when we find the product AB, and in this proof, I was just focusing on one element, right? So I'm saying you take, let's do this with a cute highlighter. You take a column from matrix B, I'm gonna say column J, and you multiply by a row from column A. A row from matrix A, what am I saying? Okay, and that's how you create or you find the product AB. So I'm just using an arbitrary one, okay, to do this proof. And then remember how we do this multiplication. I showed you in the previous video. I just usually write up top B1J, this column here, right? Then you would have B2J to Bnj. And then you find the corresponding products, which is exactly what I have in the proof there. You have AI1 times B1J, bam. AI2 times B2J, bam. All the way up to the last one, AIN times Bnj, like that. Okay, so that's what I'm showing. It's not the whole matrix AB multiplied out. It's just an arbitrary element from it. Okay, so we can prove the rest of this property. Okay, so me adding this, I need another little page here. Okay, so what do we say now? Let me rewrite this AB again, okay? So we had the AB, an element of, not the whole thing. So an element of AB looks as follows. Remember, it was AI1, B1J, plus AI2, B2J, plus up to AIN, Bnj. Do you remember what the heck we're trying to prove? No, you probably forgot, huh? Okay, property 4 says this is a scalar C times AB is equal to C times A times B, which is also equal to A times CB. We can handle it all in one shot. Watch this, we're so good. So if we have C times AB, that would be C times just one element of AI1, B1J, plus AI2, B2J, up until AIN, Bnj. And this would equal CAI1, right, times B1J, plus, I can distribute and regroup. These are all real numbers now. CAI2, B2J, up until CAIN times Bnj, and this would give me C times A times matrix B. Alternatively, I could also rewrite it as AI1 times C times B1J plus AI2 times C times B2J all the way up until AIN times C times Bnj. And this is A times C times B. And these are all based on using the associative and commutative properties of multiplication for real numbers, which I'm applying here to an element of the matrix AB, okay, to show what I needed. Okay, very good. I'm gonna actually stop the video here before we move on because the rest is gonna get beefy and I want you guys fresh as a daisy for part 2. Okay, so stay tuned. 2.2 part 2 is coming soon.